All right, good morning, everybody. So I hope you all had a good weekend. So today we'll continue our discussion about testing for the convergence or divergence of series. I have worksheet 17 here about the ratio and the root tests. But again, as usual, if you still have some questions about previous topics or if you have encountered some challenging questions in your quizzes or homeworks about the tests that we have considered so far, just let me know via the chat. And I look at your calendar, and it seems that you started talking about section, I guess, 9.7 this morning. So that means you already discussed the alternating series test and absolute convergence. So you're starting, I guess, with power series. So let's just go through the ratio and the root test, and then if time permits, we'll go to alternating series tests as well. I also have worksheet 18 already uploaded in my website. That's the blank worksheet for section 9 point, what was that? 9.7, I guess, about alternating series test. Okay. But I have here in worksheet 17 a link to a nice set of online notes. I think if you are reading some things, you might have encountered this tutorial site. This is a set of very good materials. I actually lifted some of the examples there for our discussions today. The nice thing about this site, he also has on Calculus 1. So if you're looking for some review materials, as well as for, he also has materials for Calculus 3, and I think ordinary differential equations, also pre-calculus and algebra. So you can visit this website there. They are very good notes. Okay, so for today, we'll look at some examples for the ratio and the root tests. Just a quick statement of this test, because I think they are basically straightforward and mechanical. So, but let's see. Maybe a quick recap of all the tests that we have. Maybe this could serve as your algorithm for testing for convergence or divergence. We have first check if your given series is one of the special series. So check if they are special series. So what are the examples of special series that we have met? We have the geometric series. We have harmonic series, P series. What else? Telescoping series. And I guess if we have this series, it's easy for us to check whether they are convergent or not. We also talk about the basic test for divergence. So this is basically your, I suggest this would be your second test to apply. If it's not a special series, then try the basic test for divergence first, because that's the easiest. You can actually do the test mentally, because you just need to take the limit of the n term as n approaches infinity. If it's if it's not equal to 0, then it's divergent. If it's equal to 0, then no conclusions can be made. Then you go to other tests, right? Last time we had the comparison tests, though I think yeah, I remember our discussion on the comparison test is a bit messy because I had some troubles with Teams. So what I did is shared with you the link of my recording with my second lab class, for which my app already worked. So, and then also I uploaded the annotated worksheet. I edited it a little bit, so you can check it out. So there we have comparison test. The idea is to either use direct comparison, wherein you need to think of a larger convergence series or a smaller divergence series. But I think it's easier to use the limit comparison test, wherein you just need to find a series that behaves in a proportional way to the given series. So yeah, and usually what you'll get would be a geometric or a P series for that. Now we also had the integral test, but I guess you will agree that this is quite a tedious test. There are two preliminary steps to be done. You need to make sure that the function corresponding to the terms of your series is positive and it is decreasing. And after that, you need to evaluate the improper integrals. So that's why I put the integral test towards the end of my list. This is my last resort for testing for convergence. What I do the next after comparison test, if comparison test doesn't work, then I'll try the ratio or the root test. This is our topic for today. And then if this will not hold, then I will have the alternating series test as my next option. So basically these are, this could be your strategy for testing for convergence or not, okay? Well, what are the ratio and the root test? These are two equivalent tests. Oops. Okay. So the ratio test. So this works for, I look at the lecture notes and I don't know how, if you define the ratio test this way. Did you take the limit of an plus 1 over an, or do you take the limit of the absolute values? Because here, if you're given the sum of an, what you, go ahead.
Sorry, I think I'm familiar with the an plus 1 over an.
Without the absolute value bars?
Yes, correct.
Okay, yeah, that's fine. So I guess in the textbook, yeah, they assume that you start with a summation of ANs, where AN is not negative. So the assumption here is A sub n is greater than or equal to 0. And then you can apply the ratio test, which tells us to take the limit of A sub n plus 1 all over AN as n approaches infinity, and take a look at this limit. So let's call the limit equal to capital L. All right. Now, if L is less than 1, then series converges. Oops. If L is greater than 1, then series diverges. If L is equal to 1, no conclusions can be made. Right, let's see what's the rationale behind these three cases. Well, the thing here is that what happens when the limit of an plus 1 over an is less than 1? Well, if the limit is less than 1, that tells us that a sub n plus 1 over an is less than 1 in the long run, right? This is for large n's. And that means a sub n plus 1 is smaller than an. This means that the next term, a sub n plus 1, is smaller than the previous one. And if that's the case, then we will get a convergent series, because eventually all the terms in our summation will become smaller and smaller and smaller and smaller. And hence we can get the finite sum. If the limit is greater than 1, that means that the terms in the series will continue on to increase. And if the terms in the summation keeps on increasing, then we do not expect to get a finite sum, right? So that's why we say that the series diverges. If the limit in the long run is equal to 1, then that means a sub n plus 1 is almost equal to a sub n for large n. Then there are two possibilities. The limit could, or the series could converge. It can diverge, right? So hopefully that gives you an intuition about these three cases. So take the limit of a sub n plus 1, and you get this by replacing all n's you see in the series by n plus 1, divided by an, and take a look at the limit. All right. Now, when is the ratio test handy, or when will it be the best test to use? Well, here this is extremely helpful when an involves factorials and powers. Okay. So if you see your summation having factorials and powers, the go-to test would be the ratio test. And equivalent to the ratio test is the root test. Well, for the root test, what you need to take a look at is the limit of the nth root of a sub n as n approaches infinity. Or in other words, you're taking the limit of an raised to 1 over n as n approaches infinity, and you get a limit L. If L is less than 1, then series diverges. If L is less than 1, the series converges. If L is greater than 1, then series diverges. And if L is equal to 1, no conclusions can be made. So they do have have the same conclusions as the root test, or same criteria for the ratio test. Yeah, sure, Herson. You can send some questions via the chat so we can discuss them. Okay, so while waiting for that, let's look at some preliminary examples. So here in worksheet 17, I have copied the exercises from the textbook. So you can browse through them and see if if there are some interesting problems for you here. Okay. Now what I'll do is to start with a quick example. Well, let me start with let's start with an easy one. Say okay, let's try this summation of 9 to the n over 2 to the n plus 1 times n. The summation here starts from, say, 1 until positive infinity. Okay. So here you see that the given expression has exponents involving n, right? So you can either choose the root test or the ratio test. Okay. So those two tests are equivalent, so you can choose between them which one would be easier. But for this case, I'll use the ratio test first. Okay. Though you could also use the the root test, or maybe I can do both. So using the root test, the ratio test first. We'll take the limit of, remember, limit of a sub n plus 1 all over an as n approaches infinity. Okay. Now, again, a sub n plus 1 is derived by replacing all n's you see in an by n plus 1. So the numerator here would be 9 to the n plus 1 all over 2 to the n plus 1 plus 1 times n plus 1, right? Look at what happened. I replace all n's by n plus 1. So there we go. The n plus 1 for the exponent of 2 was replaced by n plus 1 plus 1, right? Because I changed all n's by n plus 1. And then this n here was also replaced by n plus 1. So everything gets replaced by n plus 1. And then for the denominator, this is an. So this is basically the given term in the series. Okay. Then I'll simplify before taking the limit. This is a complex quotient. So what I'll do is to write it as a product. So 9 to the n plus 1 times 2 to the n plus over 2 to the n plus 2 times n plus 1 times, remember what happens when dividing a fraction, you can write it as a multiplication by the reciprocal of the divisor. So we'll have 2 to the n plus 1 times n all over 9 to the n as n approaches infinity, right? And then now, this is the reason why it's extremely handy if you're working with exponents, because when you form the quotient a sub n plus 1 all over an, we are expecting that some of the factors will cancel each other out. Like this guy, you have 9 to the n plus 1, and here I have 9 to the n. So that means this will be canceled by some of the factors here. So we'll just be left with the 9 in the numerator. All right. And then here I have 2 to the n plus 1. Oops. Here I have 2 to the n plus 2, so that means I will have what? I will have a 2 left in the denominator, right? Because when I cancel this, I'll have 1, 2 left in the denominator. And then what else? We'll have an n on top and an n plus 1 in the denominator. Okay, and then let's evaluate the limit. Oh, I'm taking the limit as n approaches infinity. And I have here a polynomial in n of degree 1. In the denominator, I also have a polynomial of degree 1. So that means when taking the limit as n approaches infinity, we get the ratio of the leading coefficients. Here, n has coefficient 9. If I carry out the multiplication here, n will have coefficient 2. So the limit would be equal to 9 over 2. 9 over 2 is obviously greater than 1. So by the ratio test, so the series diverges, right? Because the limit is greater than 1. So the idea here is if you have a term now, it would be 9 over 2 times larger, or the next term would be 9 over 2 times larger than the previous one. So the terms in the summation will keep on increasing by a ratio of 9 over 2. So that means there's no chance you will get a finite limit or a finite sum because the terms in your summation will keep on increasing. Okay? Now, alternatively, you can also use, we can use the root test. Well, the root test is helpful whenever you have limit of, if you have exponent n, or yeah, if n is involved in your exponent. So for the root test, we take the limit of a sub n raised to 1 over n. That's the nth root of an as n approaches infinity. So if I'll do that, I'll have the limit of 9 to the n all over 2 to the n plus 1 times n raised to 1 over n as n approaches infinity. Okay. Let me just double check if I have the right n term. Yep. So you take the limit of a sub n raised to the 1 over n, and then you'll play with loss of exponents. So now, if this guy goes inside 9 to the n, remember if you're raising a power to another power, you multiply the exponents. So 9 to the n raised to 1 over n is just 9 raised to the product of n and 1 over n. So the product would be a 1. So you'll have 9 to the first power. And then in the denominator, I'll have 2 to the n plus 1 all over n times n to the 1 over n. And we take the limit as n approaches infinity. All right. And then now let's do this. I can write this as the limit of 9 over 2 to the 1 plus 1 over n times n to the 1 over n as n approaches infinity. And let's see what happens here. As n becomes large, 1 over n will go to 0. So this guy will go, this factor will go to 2. But what is the limit of n to the 1 over n? So maybe I'll need a limit problem here on the side. So note that the limit, if you're considering the limit of x to the 1 over x as x approaches infinity, this is an indeterminate form infinity to the 0. Now what we do there is to let y be equal to x to the 1 over x, right? Take the ln of both sides. And then we'll have ln y equals 1 over x ln x, right? And take the limit as x approaches infinity. Okay. And this guy would be of the indeterminate form 0 times infinity. But I'll rewrite it as the limit of ln x over x. I guess we have seen this before. Okay. And now this is infinity over infinity. So this is the limit of 1 over x all over 1 as x approaches infinity, which is equal to 0. Thus, the limit of n to the 1 over n as n approaches infinity is equal to e to the 0 is equal to 1. maybe this result is something that you can remember, because this usually comes in. This usually arises when you are considering using the root test. So if you are dealt with the limit of n to the 1 over n, this will just be equal to 1. Okay. So ultimately here, so going back to our problem, so this would be equal to 9 over 2, right? Because here you have this going to 0, so you'll have 2 to the 1. That's how I got that. And n to the 1 over n will go to 1. So this would be 2 times 1, but 2 times 1 is 2. So that means this is greater than 1. Okay? So the given series diverges. Now, the thing about the ratio in the root test is that they are equivalent. If one of these two tests will have no conclusion, then the other will also not have a conclusion. So if you try the root test and it's inconclusive, do not try the ratio test, because that will also be inconclusive. So you need to go through another test. Okay. Now I see that there's a lot of questions in the chat. Maybe I'll go take a look at them rather than look at the examples I prepared. I guess this would be much helpful. So let's see. Okay, first one is from person. This is the sum of k factorial over 21, 6 to the k. I think, okay, actually the starting k doesn't matter here. I'll assume that we start at 0 to infinity. Though, yeah, sometimes you won't see indices of summation. That just means that the starting value for k is not important, because if two series differ only with the first few terms, then they will either both converge or diverge. That's why sometimes we drop the index of the summation. Okay. Now, what do we see about this series? So, well, you see here in this series that you can try basic test for divergence, right? K factorial grows, actually this will grow faster than any exponential function. So that means by the basic test for divergence, I know that this will diverge. Because if I take the limit as k approaches infinity, k factorial grows a lot faster than the denominator. So that means the limit is equal to 0, so this would be divergent. Okay, but maybe this is under your homework for the ratio or the root test. So if you were told to use the ratio and the root test, then you won't have a choice but to do it. And here I see there's a factorial involved. If there's a factorial involved, there's a big chance that the ratio test would be extremely helpful. All right. Hersen has a quick question here. I'm not sure if they will give you the index of the summation in the tests, but if they don't give the index of summation, that's fine, right? So because you can just ignore the limit of summations, it doesn't matter where the summation starts. It will have the same behavior as this will have the same behavior even if you start at k equals 0, k equals 1, k equals 2, and so on. And actually, our tests doesn't care about the starting index for the summation. So you can start with any finite value, and the same test will apply. Right? So it doesn't matter usually. Okay, so let's see. Actually, it will just matter for tests that require the function to be decreasing all throughout or alternating all throughout, but not a big deal. So probably that's why they just omit the index of summation. Okay. All right. So for this one, as I've mentioned, there are factorials involved. So chances are the ratio test would be extremely handy here. Remember, for the ratio test, we take the limit of a sub k plus 1 all over a sub k as k approaches infinity. Again, the numerator is formed by changing all k's you see here to k plus 1. So instead of a k factorial, I'll have a k plus 1 factorial all over 21 to the 6 times k plus 1. All k's were replaced by k plus 1. All over, I'll just copy the k term. So k factorial over 21 to the 6k. Take the limit as k approaches infinity. And you see here why the index of summation doesn't matter, because we are only interested what happens when k becomes very, very large. So it doesn't matter what are the first few values of k. What we're after would be the behavior as k becomes extremely large. Now we simplify the complex ratio here, or the complex fraction. So I'll have k plus 1 factorial all over 21 to the 6k plus 6, and then times the reciprocal of the denominator as k goes to infinity. Okay? And then the reason why the ratio test is helpful here is because there would be nice cancellations between the factors. So here I have k plus 1 factorial. I can cancel some of the factors with a k factorial below. Because remember, this guy means k plus 1 times k minus 1 until you reach 3 times 2 times 1. Meanwhile, k factorial is k times k minus 1 until you reach 3 times 2 times 1. So you can cancel everything here, cancel everything there. So there will only be a k plus 1 left in the numerator. Okay. Right? So I hope by now you're familiar with expanding factorials, because that's our go-to technique for the ratio test whenever there are factorials involved. All right. And then what's next? 21 6 to the k, that will be canceled by 21 raised to the 6k. So there would be a or 6 remaining in the denominator, right? After you cancel this guy with some of these. Okay. And I guess we have that. What happens when k becomes very large? So this would be infinity. So the form here would be a large number divided by 21 to the 6. So this will still be a very large number. Okay. And obviously this is greater than 1. So therefore, the series diverges. Because the limit is infinity, which is basically larger than 1. All right. Question, Daryl?
Yes, I have a question. So
Uh-huh.
because we had the infinity over the number, it was infinity, but if it was the number over infinity, it would be 0, correct?
Exactly. Yep.
Okay. All right.
And
Thank
if
you.
that case, the series would have converged because
Okay.
0 is less than 1.
Okay. Thank you.
All right. Our Herson infinity, this test will apply if the limit is infinite. Okay. So the only exception to the ratio and root test is when the limit is equal to 1. If you get a number, formal, a real number or a formal number like infinity, then the the series will diverge. Okay, this will tell us that in the long run, the ratio between the current term and the previous term will be very huge. That means the terms at the latter part of our summation will keep on increasing at a much faster rate. So that means there's no chance that we will get a finite sum. All right. Or perhaps that's why you had some troubles with those questions you sent, right? Yeah. Okay, the only exception again for the ratio in the root test is when the limit is equal to 1. Otherwise, it will be converged. Otherwise, you'll have a conclusion. If the limit is less than 1, including 0, right? So that means it's convergent. If it's greater than 1, it's divergent. Okay, let me see. Okay, let's try problem 3 here. Oh, by the way, are these from the written homework or from an electronic homework? Because if so, I should have not been. Okay, but this will not update, right? The questions will not update if you retake it another time. So I think I should not be giving you the answering the exact questions. But anyway, what's done is done. Just don't mention it to Dr. Almas. No, just kidding. So let's see. Let's try k to the k to the 10th all over pi to the 4k. Okay. So let's don't worry about the index of the summation. Let me see. Here we see that the denominator has a power k. So maybe here I can try what? Maybe I can try the root test for a change. You can also, I think you can also use the root test here. But sorry, you can use the ratio test here, but I'll try the root test because the root test will be helpful here because I don't have any factorials. If it has a factorial, then automatically your go-to test would be the ratio test. If k appears in the exponent and no factorials are involved, perhaps the root test would be easier. Okay, so here I'll use the root test. Though they are equivalent, so I guess the ratio test will also apply. I just think that the root test will be easier. Because for the root test, we'll just be taking the limit of a sub k raised to 1 over k as k approaches infinity, right? And then a sub k is the given term in the series. Raised to 1 over k. And then I'll play with the loss of exponents here. This power will go on both the numerator and the denominator. And since both numerator and denominators are power themselves, so what we do is to multiply the exponents. So for the top, I'll have k to the 10 over k. In the bottom, I'll have pi times 4k over k as k approaches infinity, right? Then here I'll have limit of k to the 1 over k raised to the 10th. I'd like to write it this way. I'll tell you later why. Okay, I'll just reorder the powering, right? And here in the denominator, I'll have pi to the 4th as k approaches infinity. Good. The reason I want to write the numerator this way is because I already know what the limit of k to the limit of k to the power 1 over k. Remember, I solved that earlier. I think I enclosed it in a red box there. If you have a variable, as the variable approaches infinity, the limit is 1. And that's what I have here. The only thing here is that the variable is just k. So I have k raised to 1 over k as k approaches infinity. By my previous solution, this goes to 1. 1 raised to the 10th power will also go to 1. So top goes to 1, bottom goes to pi to the 4th. Definitely pi over 4 is greater than 1 because this is 3.14159265 and so on. You multiply it to itself 4 times. This will definitely be greater than 1. So the limit here is less than 1, right? So by the root test, series converges. Okay, is that right? So maybe we can have this this note. For any constant a greater than 0, the limit of n to the a over n as n approaches infinity is equal to 1. So this will be extremely helpful whenever doing the root test, right? And then the solution here is L'Hopital's rule if you want to prove this, but I guess I have shown that earlier. Okay. Are the tests making sense? And the solutions? Let me see. Okay, good. How about the others? Oh, I love that new feature with Teams. That's the first time I saw it. You can the your reactions or emoticons are now flying on my screen. That's great. Okay, so Morel sent in this question. Let me see. What number are we on? Number 4. Oh, by the way, I just saw homework number 4, so I will start grading my share of homework number 4 later. The thing is, it's a very long homework. I guess you have 26 problems in there. So I hope I'll be able to finish in a couple of days for that. 3K LNK quantity squared too. And why this converges or diverges. Yeah, these two tests, the ratio and the root test, are very straightforward and mechanical in nature. So as long as you have exponents and factorials, they would be nice. It's nicer definitely than the integral test. It's also nicer than the comparison tests because for the comparison tests, you should have a testing series, right? But these guys, they stand up on their own, just calculate those limits and you're good. The only drawback is that if you get a limit equal to 1, then you have to go to other tests to have the right conclusion.
I was trying to use the LCT and compare it to the 1 over k, but the 1 over c diverges, and the answer is supposed to be converges. So I'm not sure how come it does that.
Let's see.
This
Because
is
what?
this thing, by the way, which most of the questions I think you can answer them, but with P series. But with this one, I just had no clue how to solve for it.
Right. So what I'll do is direct comparison test here, and then I'll eventually use what do you call this, a P series. Person is also suggesting the integral test. I think yes, you can use the integral test because you can let u to be ln x, and then you have the 1 over x for your du. That's fine, but as I mentioned, I am reserving the integral test as my last resort. I'll try comparison test first, but you're right, integral test can apply here. I'll compare it with a series with a much simpler components to it, and let's see what happens if this is possible. So I'll copy the numerator, I'll leave the 3k, and I'll deal with ln k quantity squared. One thing we can note is that, let's see, ln k is it's smaller than k, right? Because ln k, that's the exponent to which you will raise e to get k. So definitely it's smaller than k. So that means I can replace ln k by k, and this makes, this makes the denominator larger, right? So ln k is larger, ln k is smaller than k squared. So the new denominator now is larger, thus the fraction is much smaller. So this guy is greater than or equal to. All right. Now, but will we have a conclusion? Well, what do we see here? Here I'll have 2 over 3k cubed, which is 2/3 times 1 over k cubed. This is a P series with P equals 3. So this is convergent. So what I have here is a convergent testing series. And what I'm saying here is that the given series is larger than a convergent series. Unfortunately, the recomparison test is inconclusive. So I cannot use this comparison. But what can I do here? Well, I can just ignore the ln k because this ln k will be larger than 1 when k is what? When k is greater than e. So basically, okay, note that ln k will be larger than 1 if k is larger than e, right? Because ln of e is equal to 1, ln is increasing, so if k is greater than e, then ln k is greater than 1, okay? So if it is greater than 1, what happens when I just disregard the ln k, which is greater than 1? That means I made the denominator smaller. Oh, I will not have a conclusion again. I'll have the denominator which is smaller, right? So that makes the fraction larger, and this would be less than or equal to. So what I did here is what? This is divergent, a divergent harmonic series, right? Or this is divergent because it's a harmonic series. And what I have here is a smaller divergent series, which is, this is smaller than a divergent series. No conclusions can be made. That's a bummer. But let's see. What would be a nice test? Well, oh, another trick is here. I know that this would be. Mhm, I'm thinking of having a substitute here that has a k. Let me see if this will work. So I have, okay. Note that ln k is smaller than k. That won't be conclusive either. Huh. I guess Daryl's, Herson's suggestion would be the one that would be applicable here. It seems that I need to use the integral test. But I'm trying to get a way out of it. Yeah, I guess you need to use the integral test here really. Or let me just see our previous notes here. Because I'm really trying to get to go around the integral test. Hold on, but I think we have. Okay, so last time, I guess we tried this guy, sum of 1 over n ln n, and we have shown that this is divergent. But this guy would be what? This guy would be larger than what we have, which is divergent, smaller divergent. Yeah, that won't work. So I guess really here you'll need to use the you'll need to do the integral test, right? So yeah, because comparison tests are inconclusive. So here try the integral test. Okay. And that's the same thing for the last problem you sent, Morel. You have k times e to the minus k squared all over 2. You also need to use the integral test for that. But I guess that for that problem, it's very similar to what we did last time. Let me go back to that worksheet. Yeah. Yeah, that's very similar to this one, except that you have a denominator 2 and you use the variable k. So here I used the integral test and I was able to show that it is convergent. So I guess your series will also be convergent because it is just 1/2 of the series I have in worksheet 16. All right, is that fine? Yeah, so since this is an integral test, will it be okay? I only have 5 minutes, so will it be okay if if I'll just leave this the integral test to you?
Yeah, I'm doing it right now, but thank you.
All right. Yeah, I thought comparison test will help here, but it seems that it won't. Yeah, I thought that would be that easy, but yeah. Okay, let me see if there's another question here. Okay, there's also one. Okay, person sent another question, which I guess is interesting. So let's try this one. 4 times 8 times 12 times 4k until times 4k all over 4k factorial. And we want to see if it will converge or not, right? So here you have factorials and a bunch of factors in the numerator. So let's try the ratio test because I'm imagining what will happen when I do the expansion. There's a lot of things that will be canceled. So here I'll use the ratio test. And remember, for the ratio test, we want to take the limit of a sub k plus 1 all over a sub k as k approaches infinity. And I'm hoping that the limit is not equal to 1, so that we'll have a conclusion. Okay. Now, a sub k plus 1, we replace all k's that we see by k plus 1. So here I'll have 4 times 8 times 12 times 4k times 4 times k plus 1, right? So because I needed to change all k's to k plus 1. So here, the products in the numerator will not end at 4k because I'm replacing all k's I see by k plus 1. So it will end when I have 4 times k plus 1 all over. Be careful here. All k's will be replaced by k plus 1. So I'll have 4. Oops, I'll have 4 times k plus 1 factorial. Okay, so because 4k is inside a factorial, so this guy will have 4 times k plus 1 inside a factorial all over the nth term. So I'll have 4 times 8 times 12 until 4 times k all over 4k factorial and take the limit as k approaches infinity. Now I will write it as a product and see what cancels. So I'll have 4 times 8 times 12 until 4k times 4 times k plus 1 all over 4 times k plus 1 factorial. Or basically, I can expand that. I can write it as 4k plus 4 factorial times 4k factorial, or 4k inside a factorial, all over 4 times 8 times 12 until 4 times k. Okay, let's see what cancels. Here until here, they will all be gone. Okay, so that leaves us with a limit of 4k plus 4 on top, right? And then this guy is what? This guy is basically 4k times 4k minus 1 times 4k minus 2 down to 3 times 2 times 1. Okay. Meanwhile, this guy is 4k plus 4 times 4k plus 3 times 4k plus 2 all the way down to maybe I should show you what happens here. So I'll have 4k plus 1 times 4k times 4k minus 1 all the way down to 3 times 2 times 1. All right. Then let's see what cancels. Here I'll have from 4k down to 1 will be canceled. From 4k down to 1 will be canceled. So in the denominator, we'll be left with 4k plus 4 times 4k plus 3 times 4k plus 2 times 4k plus 1. All right. Take the limit as k approaches infinity. Oh, I still can't cancel 4k plus 4 with this guy. So we'll ultimately be left with a limit of 1 over 4k plus 3, 4k plus 2 times 4k plus 1 as k approaches infinity, right? What happens here when k becomes very large? This is a large number. This is also a large number. This is a large number. So the denominator goes to infinity. Numerator is a constant 1. 1 divided by a large number, this will go to 0. And 0 obviously is less than 1. So by the ratio test, the series converges. Okay? Now, I hope now you see when the ratio and the root test are handy. The ratio test would be extremely helpful if you expect some things to cancel each other out. So that means if your given series has factorials in it, if it has a lot of products in it, or it has the exponent k or n, while the root test is extremely helpful if you have n's in the exponent. Oh, sure, yeah. I can actually show you the entire solution there. Okay. All right, any questions on that? So it seems it's difficult to expand or to find a pattern here. All you need to do is to break it down into into its smallest details and do the expansions carefully. Oh, Daryl, you have a question?
Yeah, sorry to interrupt. So, just looking at the steps. So that factorial we had in the bottom. So you're saying that because it'll infinitely go on to like 3 times 2 times 1, that it tends to 0. So the whole thing would be less than 1, and that's why it converges, correct?
Well, actually, upon simplification, I won't go down to 3 times 2 times 1, because if you see here, I expand the 4k plus 4 factorial, and I canceled a bunch of factors because I have a 4 factorial in the numerator. So essentially, what happened is upon cancellation, all right. So here, 4k plus 4s were also canceled. So essentially, the ratio boils down to this guy. And this is 0 because when k becomes very large, 4k plus 3 becomes very large, 4k plus 2 is also large, 4k plus 1 also becomes large. So the denominator becomes very, very huge. 1 divided by a large number, that goes to 0.
Okay, I see
that. Yeah, though you need to simplify first and cancel all the factors, because it would be hard to see what will happen if you have a 4k plus 4 factorial. It's hard to imagine how 4k plus 4 factorial behaves compared to the complicated numerators. That's why I had to simplify things to cancel as many factors as I can in order to get at this nice form, which is clearly 1 divided by a very large number.
Thank you.
All right. Okay, so I guess that's a nice time to stop here. Yep. Yeah, so on Wednesday, we'll start talking about the alternating series test, and hopefully start with power series. Have you started with power series today?
Yes, we did in Alma's lecture.
Okay, sure. So yeah, alternating series test is also mechanical, so probably we can do it quickly. But again, if you have questions or you encounter some things from the homework or quizzes, let me know on Wednesday, and then we'll talk about it. All right. So thank you guys for coming today, and let's see each other again on Wednesday. Bye, guys.